Today, I have the distinct honor of welcoming Dr. Alex Lidow to the C-Suite Spotlight. Alex has earned many accolades during his career in the electronics industry, too many to list actually, but I'll gladly highlight a few. He had an amazing 30-year run at International Rectifier, which, interestingly, was founded by his grandfather and his father, Eric Lidow. Alex rose through the ranks from R&D engineer all the way to C-suite to becoming a CEO. Over 3 decades, he has made numerous contributions to electronics and semiconductors, ranging from co-inventing the HEXFET power MOSFET, additionally having over 20 other patents for silicon and GaN power devices, co-authoring the book GaN Transistors for Efficient Power Conversion, which has become a go-to textbook for engineers and engineering leaders. His technical publications have been peer-reviewed hundreds of times, and he's even been requested to appear before Congress as a semiconductor industry expert. With all of these achievements, the best is still ahead. He co-founded EPC in 2007 and is currently shepherding the company as CEO, helping them usher in a new wave of innovation in power-efficient GaN-based semiconductors. Alex, I'm thrilled you can join me and can't wait to learn more about what you and your team are doing. So without further ado, welcome.
Oh, thanks very much. That's quite an intro. I'm not sure I deserve half of it.
Well, it's all accurate, so I can say it's definitely well deserved. But definitely thanks for being here. Let's go back to the very beginning. It seems like becoming an engineer was in the cards from you, almost like being part of a family business. What really got you interested in engineering such that you would dedicate your life to it?
Well, certainly my father played a big role. He founded this company, International Rectifier, and he was an engineer's engineer. He was actually educated in Nazi Germany as a Jew, which had its challenges, and always had the engineering spirit. So while I was growing up, there was always stuff to build and tinker with and stuff of interest. When I was 15, he brought home a basically a shell of an old car and said, "Why don't you make this electric?" Actually, along with some help, certainly, built an electric car and drove that for several years. And that was back in the late 60s, early 70s. So those were inspiring things. I wanted to be an aeronautical engineer, and I went to Caltech because they were the best at aeronautical engineering. But I had a professor by the name of Jim Meyer who taught solid state physics. And he truly inspired me. From that point on, I was sold on material science and semiconductor physics. That really launched me in the path that I'm still on today.
Wow, that's cool. Yeah, going from aeronautical to the materials, that's a very, very interesting pivot. Very cool. You've seen many technology trends come and go. When did you first recognize the potential of GaN, and what made you believe it wasn't just a trend, but really a semiconductor material that would be transformative?
Yeah, I guess it started back in grad school in the mid 70s when I went to grad school at Stanford. It was, certainly the center of Silicon Valley, and it was all about silicon. And I thought, well, I want to get ahead of silicon, so I'm going to work on compound semiconductors. And I worked on gallium arsenide. Got my PhD based on work there. But I realized gallium arsenide was definitely not going to replace silicon, so I went straight to silicon and I started working on what became the power MOSFET. But I always had in the back of my head what were the benefits and limitations. I was a material scientist as well as a device physicist. And when silicon hits theoretical limits right around the turn of the millennium, um, I thought, wow, we've got to find out what's next. And I read about a development in Japan where they had grown gallium nitride on a standard silicon wafer. And I thought, wow, that eliminates some of the major limitations of gallium arsenide. First of all, by having just a thin layer of compound semiconductor, you eliminate the cost associated with growing a solid crystal of something that's very, very difficult. And secondly, gallium nitride has a tighter bond between the gallium and the nitrogen, so it can withstand higher temperatures in processing, more like silicon. And that set me on the path that I'm on today. I thought, wow, GaN can replace silicon. It has much better semiconductor properties, and it can be built just like silicon. So I don't have to reinvent the infrastructure that we developed over many years for silicon.
Yeah, that's interesting to know the nexus of kind of the thought origination. Very interesting. Um, kind of on that same tip, but tell us about some of the macro technological changes that you see affecting power delivery and power management today.
Well, certainly, GaN, by the way, is still 100x away from its theoretical limits. So, what can it do if it gets to its theoretical limits? What can transform how we convert electricity and how we use electricity? So that's good. But what are the barriers along the way is the issue. And one is current density. We're really pushing incredible limits on how much current we can push through a tiny little device. I mean, we've pushed 3 kilowatts through a device that's zero point 0.8 square millimeters, and that's heating things up to 400 or 500 degrees centigrade. GaN can take those temperatures, but getting that current density to something else that's useful is difficult. So those are challenges. Also, heat extraction. We've got a lot of heat generation. We've got to figure out how to more efficiently extract it. Those are incredible challenges, and I met those in the power MOSFET world where we got to theoretical limits. I'm sure we can get it to GaN. We can do the same in GaN, and when we do, it will enable some amazing new things.
Very, very cool. With that in mind, I mean, how is efficient power conversion poised to solve those challenges?
Well, first of all, I never give up on theoretical limits. So, if there's a will, there's a way. It sounds a little trite to say that, but each one of those barriers, getting from where we are today, we're already 10x better than silicon. Getting another 100x out of it sounds like an insurmountable problem, but you just do it step by step. And the two key elements are number one, you have to have short cycles of learning. When companies take 6 months to do an experiment, your forget curve is more than your learning curve, and it's not very exciting. But if you can try something and see the result very quickly, that's that's energizing, and it gets you there faster. So we focus on very short cycles of learning. We use labs in universities. We, of course, incentive all of our foundries to be very fast on the cycle times for our development, and we have stratified R&D. We have a group of people who are looking at stuff that is leapfrog ahead of where we are today in product. And you put those together, and you really can, and as long as you have a tight understanding of the challenge, you're not just throwing money and do new things. You can make progress, and it's quite remarkable the innovation that comes out of that.
Very, very interesting. Yeah. What I've noticed and what I've heard from other people in the market is just those cycles of R&D, like you mentioned, can be quite some time. And I've never heard it phrased that way with regard to it's easy to forget stuff if you're not going fast enough, but also being efficient, which obviously is a reason why that's in the title of your company or the name of your company. As a follow up to the previous question, I think before that about trends, what would you say is one macro trend that you would see coming over the next couple of years that you don't really think other executives in your space or any space for that matter have really caught on to just yet?
So, a year ago, I would have called myself goofy for saying this, but now I've become convinced, and it's humanoid robots and the derivatives that come from that. It's not just robots that look like humans, but all of the things that are very humanoid in nature and have a certain degree of autonomy and dexterity and mobility. And the reason I say that is that there's a lot of noise now about low birth rates in all of the developed world, and the aging of the population that isn't being renewed by working age people. And so that means that there's a long-term need for a humanoid robot that can actually do some of the tasks that will no longer have people that will want to do. Certainly functions in warehouses, fast food, maybe even healthcare at home, and I think that that's a big trend that, coupled with AI, is going to be important for our future. If we look back 50 years from now at what happened this year, it's going to be an inflection point in both AI and the humanoid robots that came from there.
That's fascinating. Yeah, obviously, yeah, didn't expect that answer to go in that direction, and it from the scientific standpoint that you just brought up, and how you kind of took fact and brought that through. That it's there's the other half of that that's going to be interesting of the the layman or the non-scientist fear around all that, and how it's messaged as that becomes more successful and even commercialized. So a lot of moving parts to that. That's for
Yeah,
sure.
and I think the social issues are significant. They're significant for AI and they're significant for humanoid robots, and we need to try to get in front of them. Not that that's something that we're particularly good at, but the trend is there,
Yeah.
and we can't put the genie back in the bottle.
Yeah, no, absolutely. Tell us about the company's mission, and assuming EPC is successful, what impact do you believe you will have on society as a whole?
So our mission, which we stated on day one, was to make power devices in gallium nitride that are higher performance and lower cost than silicon. We've been true to that. I think we've succeeded in that, but now the test is going even lower cost, even higher performance over time. And that will be successful. Hopefully, EPC will be able to harvest that success. My father had a favorite saying. He said, "The future is easy to see. It's just hard to see when it's going to happen and who's going to benefit." So I'm hopefully trying to make the future and benefit from it. But I think that one of the biggest impacts that GaN and EPC will have will be enabling autonomous mobility. Humanoid robots are one example of it, but we have autonomous vehicles. We have these last mile delivery vehicles. We have drones. We have all sorts of autonomy and intelligence married together. And EPC is on many different things on those autonomous vehicles. For example, LiDAR systems. Those are the light detection and ranging that can see. Robotic vision is heavily dependent on LiDAR, not cameras, LiDAR, because LiDAR gives you the essential information on what's around you. Motor drives. There's 40 motors on an average humanoid robot, and they have to be not only efficient, but they have to have the ability to do high torque, high speed, high precision, and be in a very small space and be very efficient. So that's another area. And then finally, there's AI. And EPC's GaN is every electron that goes through an AI system goes through an EPC GaN device. So we are part of that, and the role that we play in AI is trying to mitigate this incredibly consumptive energy thing called AI, where just the amount of energy it takes to do an AI thought is huge compared to just a Google search, and you need to mitigate that. So we make that power conversion delivery much more efficient. So autonomous mobility is going to be a critical thing in our future, and we are in all different facets of it.
Yeah, and it's interesting that consumptive part. Yeah, really, it's just such a theme that we hear, that I hear even personally from engineers talk. The word bottleneck, I probably hear a few times a week minimum on problems that they're either trying to
Sure.
solve, or the interest for an engineer that wants to maybe move into the AI space from power.
Yeah.
That bottleneck concept is just the top of everyone's mind, for sure. Um, can you share a specific customer success story, or a deployment of EPC's technology that has been most impactful to you and or your team so far?
So we launched our first devices in mass production in March of 2010, and sometime in the subsequent 6 months, I got a call from a guy named Dave Hall, and he had a company called Velodyne. And he explained to me, he said, I want to build a light detection ranging system that can compete with radar. Radar has a certain resolution. LiDAR, which just fires off a bunch of photons and then they reflect back and you measure how long those photons have been out there, could be a better way to do that. But the problem is we don't have the technology to make a large enough packet of photons that are tight enough in distribution that you get high resolution at long distance. And he said, I think GaN can do that. And he started designing with our GaN devices. He was probably the first. And LiDAR, modern LiDAR was born out of Velodyne and out of Dave Hall's head. And it was the cross the chasm application for us. It's the first thing that went into volume production. Of course, LiDAR became quite famous. It went through a hype cycle, and it enabled initially Google mapping, and then it went straight to autonomous vehicles, and from there into robotics, into collision avoidance systems, even into those little robotic vacuum cleaners that so many people have. And that really launched us on a path. We knew we had something impactful at that point, and it was thanks to Dave Hall's vision.
Interesting. Yeah, no, the LiDAR bug was definitely, it still is. It was hot for a long time there, and very, very cool. Conversely, so kind of flipping that question on its head a little bit, GaN, and if anyone hasn't picked it up, if they're listening to any of this, GaN's tough. It's tough. You guys have been around long enough to figure out some things. I mean, that example right there with Dave's company there, but about developing and selling GaN through trial and error. Tell us about one of the early mistakes and what you learned from that.
Yeah, I'd say the early mistake was I thought it would be if you made a device that had the similar three terminal characteristics to a MOSFET, that engineers would feel it's easy to replace their MOSFETs with our GaN devices, which were clearly superior in performance and size. Why wouldn't they do it? Well, it turns out that was a huge underestimation. It was an underestimation from many different angles. People's reluctance to change unless they have a strong motivation, and the motivation needs to be they can't do it any other way. They are reluctant to change because they don't understand the change and are therefore afraid to make a mistake. They don't want to change because they don't trust the new technology or the new device because maybe it's not reliable. Maybe it's got some hidden quirks that they don't understand. So we really underestimated that and had to, and the learning from that was how much we had to invest in education. And that was, initially in application notes and field applications engineers, with limited ability to afford, we had to put all the energy that we could into that in order to have adoption of our devices. And eventually we started writing textbooks that were peer reviewed, started to appear in universities. And today, I would say we have enough skilled engineers, enough success stories, and certainly enough data to show that GaN is much more reliable than MOSFETs. That now those barriers are gone, and it becomes more a cost barrier, meeting an open design window.
If you're on the talent side and you are a GaN engineer and you've been talking to somebody that's developing MOSFETs, there's a reason why they hesitate on that, or vice versa. If you're developing MOSFETs and you want to move into GaN, there's always, I get to see that hesitation all the time because of those problems.
Yeah.
Switching gears a little bit and talking about trajectory of the company and longevity of the company so far, I believe it was Oscar Wilde who said, imitation is the most sincerest form of flattery. And you've basically been around long enough to not only have success but to be imitated. And you recently defended and won a patent infringement suit. What advice would you give other startup leaders about safeguarding their IP?
Yeah, look, I have a lot of long and hard experience on that. Our power MOSFET patents were also fundamental, and we had to defend them in court 8 times, I think 18 times on appeal over a period of 20 years. And eventually we won all of those. And eventually we licensed over 25 competitors. So, number one, I would say that don't be enamored by numbers. If you have 500 patents, it may be worthless compared to one good patent. It only takes one good patent. And if you've got a few good patents, that's even better, of course. But don't be enamored by the number of patents that somebody has. It's not a metric that's of value. And in order to have really fundamental patents, you have to be in at the beginning, right? So if you want to protect your IP, I'll give you some easy tips on that. But really, if it isn't very good IP, it doesn't matter. So if you're in at the beginning, you can get fundamental patents. If you're in at the later stages, you're going to get incremental patents, which will have incremental benefits, probably more defensive rather than offensive. In other words, you can trade them for licenses as opposed to a fundamental one, which as in our patents, you can actually win in a court. There are four key elements that I found over the years are important to having a very good piece of IP. The first one is a good invention. If you don't have a good invention, IP doesn't matter. The second is having a good patent lawyer that can write easy to understand yet thorough patents. If the inventor can't understand it, because there's too much legalese or too many I'll say spaghetti like phrases and things, it's not a good patent. It needs to be easy to understand, and that takes a good patent lawyer. The third is, if you want to safeguard your IP, you have to be prepared to do it in court, and that means you need a good litigation team, and they're expensive, so you have to have the money for a good litigation team, unfortunately. And hopefully you don't get through litigation. That leads to the fourth important thing, and that's a good negotiating team for licensing. Uh, and my experience, litigation teams are not good negotiating teams. So you really need somebody who has a strong sense of negotiation, not a strong sense of litigation to do that. So those are the four things: good invention, good patent lawyer, good litigation team, and a good negotiating team.
Awesome. That's great information. And yeah, if only those processes were a lot faster, but they take time. The legal
And
process.
money,
Yeah,
and a
yeah,
lot of
yeah.
money.
Yeah. Those hourly rates that the attorneys are charging, especially if you're in the Bay Area or Silicon Valley, yeah, that's a whole other discussion. But I'm gonna bring something up that kind of flies somewhat in the face of your philosophy on patents, because I'm gonna kind of brag about you guys for a little bit. But my next question is kind of prefaced through patents. But EPC has developed an impressive portfolio. I'm going to talk about quantity here of over 200 patents and 150 products. As CEO, how do you balance the quest for innovation with the need to have commercial products that help grow the business?
So there are a few stories. One of them, early Silicon story of Bill Shockley and Shockley Labs, where he was so focused on innovation that he forgot about the business, and they went bust. And disgusted engineers, the traitorous eight, founded Fairchild, later Intel. So that's the example of imbalance. Um, but you always have to have your eye on the prize. What is it that you're trying to achieve? And it needs to be a commercial product. If it's not commercial, it's frankly, an academic effort. So what we do is we have a small strategic effort with very short cycles of learning. Just a few people, and they work in university labs that are very capable. So we get very fast cycles of learning. We have very flexible capability. And then we have a large development effort. And those are the people that actually have to make products. And we've got to tie them together constantly. And we do that all the time. So it's really short cycles of learning at all steps, but having a small strategic effort with a large development effort. And then, of course, anytime you see something that has a spark, you need to protect it with a disclosure. And then, if that spark grows into a flame, protect it with a patent. And if that flame looks good, go global with the patents in as many strategic countries as you can, and realize that every time you do that, you're incurring more and more expense over time.
Oh, great. That's yeah. Easier said than done, but very, very cool. Thanks for
Yeah,
walking us through that
it
process.
is.
Yeah. Shifting gears, building a startup, especially a semiconductor company, isn't for the faint of heart. What challenges do you remember that kept you up at night in the early days? They may still keep you up at night when you founded EPC.
Yeah, for one, I know several people that started companies, and they all say about the same thing. If I knew how hard it is, I probably wouldn't have done it. I wound up starting a company in my 50s, and it was I'd say that's a young person's job, but I was in my 50s and in good health, so why not? Um, the thing that kept me up at night in the early days was making a working prototype before we ran out of money. That was a fun. I had very limited access to funds, and we had to get to a prototype. And I used to drive my wife crazy, saying, we've got to get to product, avoid dilution. And she was tired of hearing that, and still reminds me of my repetitive nature in that. But then the second one is now you have a working prototype. You can usually attract funds from that, and then the next thing, which hounds me to this very day, is running out of money before generating cash. You can always go broke if you don't generate cash, and cash is the key to independence. So that has to be the eye on the prize, and until then, you're definitely at risk.
Absolutely, and part of the challenge there is getting the people to in house that are gonna help usher that cash development or the making of revenue, and that's kind of where the double E's and the smart engineers you get to bring in come into play. And so, I mean, with colleges and switching over to talent a little bit, producing fewer double E's every year and consolidation within our industry, competition for talent has never really been greater. How does EPC compete for and manage to attract top engineers?
First of all, GaN is an exciting new area of exploration innovation. There's a lot of noise around it, and so that attracts ambitious, people who want to get in front of the world, in advance of where we are today. And so that's an important thing. If you're making something dull, I don't know, cookies or something like that, you're not going to attract top engineers. You're just not going to. And so that's one, have an exciting area and make sure that people understand why it's exciting. But then the next one is you have to be exposed to students. And we do that through several things. We do a lot of presentations at various conferences all over the world, all the time. We've got, I think, 30 PhDs. We write peer review articles, and we go to conferences talking to them, and those are where you can inspire students. And then probably one of the best things is we wrote the only peer reviewed textbooks in this field. Gosh, I got one right here, just in case we can do a shout out on this one. But this is in the third edition. Let's see, front there, and it's in October, coming out in the fourth edition. And that's what kids in school learn by, and so they're learning, if you will, they're learning the EPC way with GaN, and I think that that's certainly a nice way to attract top talent, and we have been able to attract top talent.
That's great. That's great, and hopefully you can make the publishers happy on that side as well. So that's good.
Well,
Um,
they've gone through it 4 times, so I guess they're happy, right? This
I
is
would,
the
yeah,
fourth
you would
edition.
assume so, right? um, so, easier question or tougher question depends on how you look at it. Over time, you've been at the helm here for quite some time. How have you managed to keep your team marching toward the same vision for nearly 2 decades? And how has your leadership approach evolved over time?
I think one way of keeping a team marching toward the same vision is to have consistency in the vision and also continuous communication. People have to understand the progress towards that vision. How are you doing? If the vision is higher performance and lower cost compared to silicon MOSFETs, how are we doing on that? Well, let's look at cost, let's look at performance, and let's look at how the MOSFETs are doing, because they're not standing still. So that is important. We get together as a company certainly virtually every couple of weeks. We have, every 6 months we all get together. So there's all sorts of things like that along the way. But people have to see the consistency that you walk, you walk the talk with what you're doing. Now, in terms of how has it evolved over time, I had to adapt many times. I started off in the late '70s as an R&D engineer, working as an individual to develop new stuff. And I went from there into manufacturing, into sales and marketing, CEO. And then I got fired. I lost my job abruptly. And so, there I was in my 50s without a job, and I had to start from scratch again as an R&D engineer. And that meant, hitting the books, learning all the things I'd forgotten in the 20 years since I'd been an engineer. And that taught me an awful lot about how leadership evolves and how to adapt from all the different stages. I was reminded of all the stages I'd been through late in life, and therefore I could relate back to all of them. And I think that helped me be a better leader of a startup that is really incredibly focused on evolving a new technology quickly. And I used all the skills I'd learned over those 30 years in how to do that. And they were learned at each stage. And it was very good that I was reminded of all those stages, relatively late in my career.
Cool story. Really interesting. This may bleed into this next question that I was going to ask you is, and it may not, that's okay. What's one piece of advice you learned as a founder that you would share with other startup founders to help them be successful?
Well, I'd say number one, don't get in it for the money. If you're in it for the money, you will blow out of there. It will burn you out. It will blow you out, and it will eat you up. You've got to get in it for the challenge to do something significant that will improve people's lives. As I said earlier, every successful entrepreneur I have talked to said the same thing. If I knew how hard it was in the beginning, I wouldn't have done it. So if you're in it for the money, you're going to give up or run out of money. But it is not the thing to do for money. It's the thing to do because you really have something that you can contribute that will improve people's lives, and that will propel you through the hard times. I think that's the one thing that's kept me going despite dark times.
I mean, at the end of the day, it usually does come down to passion. People do this because of passion. When they interview somebody, they meet somebody, they want to see, is this person passionate, and that absolutely comes out. That not only comes out there, but it's been great to kind of hear your story and your journey, not only from a leadership perspective, but from a technology perspective, and the insights that you gave. So really appreciate everything that you just shared with us and the audience that's going to have the pleasure of being able to kind of listen to some of these nice morsels of advice and information. So, Alex, thank you so much for speaking with us and with me. How can someone get in touch with EPC if they want to discuss partnering with the company, purchasing product, or even potentially even joining the organization?
Yeah, so I think that the best way is, contact me through LinkedIn. I'm up on LinkedIn, and if you want to connect, you can connect there. And we get quite a few solicitations through LinkedIn. I look at all of them, and there are many inspiring people that we've hired through that vehicle.
Really appreciate again you taking the time to do this. We're really excited to share what's going on at EPC. A lot of exciting things going on there, not only just in the GaN space, but the specifics of what you guys have already brought to the market and what you're continuing to bring to the market. If anyone's spending time at the conferences and trade shows, I recommend taking a few minutes and looking at what they're doing. It's pretty interesting and exciting. So thanks again,
And
Alex.
come up and visit with me. I'm at those shows too. I love to meet new people, and I love to particularly meet students who are interested in the future of power management.
Awesome. Awesome. Well, thanks so much again. Really appreciate your time, and best of luck. And we'll talk soon.
Thanks so much.